Chapter 3.5, Limits at Infinity. Day 1, Limits at Infinity and Asymptotes. First off, what do we mean by limits at infinity? Basically, what we're looking at is we're looking at the end behavior of a function. What happens at the extremely high x values or the extremely low x values? Right? And what we're looking at for end behavior, it ends up being the horizontal asymptotes. What is happening at the very extremes of the graph is the horizontal asymptote. And we symbolize this in calculus by saying the limit of the function as x approaches infinity. The limit of the function as x approaches infinity. Because that's what's happening at the extremes. X is approaching infinity. What is happening to the function? So what we'll be doing is we'll be putting infinity into these functions and kind of manipulating them. We'll start with a simple one. Find the limit as x approaches infinity of 5 minus 2 over x squared. Let's take this into two pieces. Let's first do the limit as x approaches infinity of 5. The limit as x approaches infinity of 2 over x squared and subtract results. Well, as x approaches infinity, 5 is always 5. So the limit of 5 will be 5. And then we will subtract the limit as x approaches infinity of 2 over x squared. So what we're doing here is we're taking 2 of something, let's say $2. If I take $2 and evenly split it amongst an infinite amount of people, how much does each person get? Essentially, you end up with nothing. So the limit as x approaches infinity of 2 over x squared is 0. The more you split that $2 up, the less and less you get. So this ends up being 5 minus 0, which is 5. So when we're looking at n approaching infinity or x approaching infinity, we're looking for these fractions. We're going to try and get these fractions, because anytime we can get one of these fractions, we know it approaches 0. And then the rest of it is the number. So let's take this one. Take the limit as x approaches infinity of 2x minus 1 over x plus 1. Well, 2 times infinity is infinity, minus 1 is infinity, and on the bottom we got infinity plus 1, which is infinity. We got infinity divided by infinity, which is an indeterminate form, meaning there's more work to do. What we'll do then for our more work, I'm going to take the degree of the numerator and the denominator, whichever one's higher. In this case, they're both 1. And multiply by a fraction that has a denominator of that degree on the top and bottom. So essentially, the degree of the top is 1. So I'm going to multiply by a fraction, 1 over x, where 1 is the degree of the bottom. Do the same thing to x plus 1. So the highest power, that's what the degree is. Take the highest power and multiply by 1 over x to that power. As I distribute to the top, distribute to the bottom, this is what my function, my limit, gets rewritten as. We will have 2x over x minus 1 over x all over x plus 1 over x. Reduce where we can. The limit as x approaches infinity, 2 minus 1 over x over 1 plus 1 over x. Now as we take a look, we're going to approach infinity on each piece. The limit is of 2, well, 2 will stay the same. There's no variable. We come over to here, 1 over x. If we take $1, divide it amongst an infinite amount of people, everybody gets nothing. So this ends up being 2 minus 0 up top. On the bottom we got 1 plus, again, 1 over x is 0, so 1 plus 0. This ends up being 2 over 1. So we take the top and bottom multiplied by 1 over x to the highest power and simplify, and it ends up, we got 2 over 1, which is 2. Let's try each of these three problems. The first one, 2x plus 5 over 3x squared plus 1. The highest power is x squared, so we'll multiply top and bottom by 1 over x squared. We must do that to top and bottom so that essentially we don't change the problem. For a, we will distribute, we will get 2x over x squared, which is 2 over x, plus 5 over x squared, 3x squared over x squared, which is 3, plus 1 over x squared. As we look at that, we got 0 here, we got 0 here, and we got 0 here. The only place we don't have 0 is right here, where we have 3. So what this ends up being is 0 over 3, which is 0. And our next one, again, the highest power is x squared, so we'll do top and bottom, 1 over x squared. As we simplify that, in the numerator, 2x squared over x squared is 2 plus 5 over x squared. In the denominator, we got 3x squared over x squared is 3 plus 1 over x squared. Now we approach infinity. 2, no x there, so that doesn't change. 5 over x squared will approach 0. 3 will be 3, and 1 over x squared will be 0. So we got, when we cancel our 0, or when we approach our infinity and get our zeros, we get 2/3. And in our last problem, the highest power is 3. So multiply top and bottom by 1 over x cubed. Simplify the top and the bottom when we distribute our 1 over x cubed. 2x cubed over x cubed is 2, plus 5 over x cubed. 3x squared over x cubed is 3 over x, plus 1 over x cubed. Again, as we look at this, 2 stays 2. 5 over x cubed will approach 0. 1 over x cubed will approach 0, as well 3 over x. So everything approaches 0, except for 2, so what we end up with is 2 over 0. And if you remember, when you get a number over 0, that spells no, meaning no limit. In other words, the limit does not exist. This one, the limit does not exist because the function approaches infinity, as x approaches infinity. This one increases without bounds, both with the x and the y. Now, as we take a look at all three of these, we have three distinct cases. The first case, if you look at the degree, the denominator had the higher degree. And what happened when the denominator had the higher degree is our answer was 0. If the denominator has the higher degree as you take the limit as x approaches infinity, the answer is 0. The second case, the degrees in the numerator and the denominator were the same. When that happened, what happened? Everything canceled out, became 0, and you were just left with your coefficients. And then we got our coefficients, divided the lead coefficients of the numerator and denominator. So if the degrees are the same in the numerator and denominator, divide the lead coefficients. And the last case, the degree in the numerator is higher, and this time, the denominator, everything canceled out, went to 0, And we're left with a number up top because of your lead coefficient from the top divided by 0, and the limit did not exist. So in other words, the three cases, if the denominator has a higher degree, the limit is 0. If the degrees are equal, the limit is the lead coefficients divided. And if the numerator has a higher degree, there is no limit. It increases without bounds. So let's apply it to here. This one, there's only a fraction here, and the denominator has a higher degree, so this one approaches 0. And then 2 times infinity is infinity. You can think of this as 2 over 1, and in which case the numerator has the higher degree. So this one approaches infinity, this one approaches 0, so you got infinity minus 0, which is infinity, so the limit does not exist. And for this one, take a look at the degrees. They are equal in the numerator and denominator, so we will divide the lead coefficients. The lead at the top is 5. The lead at the bottom is 10, which reduces to 1/2. So, in review, when evaluating limits at infinity, as x approaches infinity, if the degree of the numerator equals the degree of the denominator, then divide the lead coefficients. If the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. And finally, if the degree of the numerator is less than the degree of the denominator, then the limit is 0.